Today we're talking about part-of-speech tagging. So first I'll introduce the part-of-speech tagging task. I'll then talk about one particular model that allows you to do part-of-speech tagging called the hidden Markov model. We'll talk about how to estimate these models from text, how to apply hidden Markov models to arbitrary text, and then we'll work through some examples within LTK so you can tag text with part-of-speech tags. Okay, so first, what is part-of-speech tagging? The goal of part-of-speech tagging is to take each word in a sentence and apply a part-of-speech tag. So this is the most basic syntactic analysis that you can do of a sentence. But it's useful for downstream tasks like parsing, that we'll talk about in the next 2 weeks, and word sense disambiguation. So part-of-speech tags represent major categories of syntactic usage of words. One of the corpora that we'll be playing with is the Brown corpus. This was about a 1,000,000 word corpus that was really the first corpus that was part-of-speech tagged. It had almost 90 tags. Most people agree now that that's a little bit too big, and so the part-of-speech tag set that we'll be seeing the most of is the Pin Treebank tag set that has about half as many tags. If you look in the inside cover of your textbook, it has a full listing of the Pin Treebank tags. Some examples of tags that we'll see line up pretty well with what your intuition should be. We have tags for nouns, tags for verbs, tags for pronouns, tags for adjectives, tags for adverbs, tags for prepositions, tags for determiners, tags for conjunctions, tags for particles. One of the most common distinctions that you'll see in part-of-speech tags is between closed classes and open classes. So closed classes are words whose functions and meaning are fixed and have a very small number of words that fit in that set. So things like pronouns, prepositions, modals, determiners, particles, conjunctions. The words that fall into these categories have not changed in hundreds of years. Whereas the open class categories can have an uncountable number of words, and new ones are easily invented and added, and you can use them in discourse for the first time as a nonce word, and people will figure out very quickly what they mean. So Googler, textish, Google, geeky, chompingly. These are words that may have never been used before, but it's very easy to figure out what they mean when they are used. So like can be a verb or a preposition. So if you say, I like candy, that's a verb. Time flies like an arrow. In that case, like is a preposition. And part-of-speech tagging allows us to discover these ambiguities. And if we had a system that could automatically tell us whether like was being used as a verb or like was being used as a preposition, we could figure out the broad class of meaning that the word represented in a particular context. Similarly, around can be a preposition, an particle, or an adverb. And again, if we had a part-of-speech tagger that could distinguish these contexts, we could figure out more precisely what around meant in a given sentence. So how hard is part-of-speech tagging? Typically what we do to make our lives a little bit easier is we assume that we're given our input in a form where the words are broken up. And so in English this isn't too much to ask for, but in some languages like Chinese or Arabic, it's harder to see where one word ends and another word begins. Part-of-speech tagging in English isn't that hard. Only about 10% of word types are ambiguous. So that sounds good, but what isn't so good is that in terms of overall usage, not just the words in a dictionary, about 40% of use cases are ambiguous. So that's sort of the lower baseline. The upper baseline is human performance at the task. So if you ask humans to do the same task of assigning part-of-speech tags to a sentence, you'll get around 96% agreement. So you can't really expect a machine to do much better than that. Current systems do pretty well. You should expect something to be around 90% accurate on arbitrary text. And so there have been a number of approaches that have been used to solve the part-of-speech tagging problem. It began with rule-based methods where humans created handcrafted rules to try to determine, given a particular word in a context, what part of speech should be applied. That has fallen out of favor with the statistical revolution that we talked about in the first lecture. Now, most people use some sort of statistical model. There are some really complex ones like maximum entropy Markov models, conditional random fields. Those tend to perform near state-of-the-art on this task. We're going to be talking about something a little bit simpler in the rest of the class, the hidden Markov model, which still does pretty well on this task. So first, let's talk about the intuitions behind the hidden Markov model. So a hidden Markov model is a lot like the finite state machines that we were talking about in the second lecture. But what's different is that instead of a deterministic process, we apply a Markov assumption, just like the Markov assumption that we talked about in language models in the third lecture, to the state transitions. And in this case, the states of our finite state machine correspond to the parts of speech. And so this gives us a generative model for sequences, which are actually sentences. Our model moves from state to state, part of speech to part of speech, under a Markov condition. So there's a transition function that takes us from one part of speech to another, and this is probabilistic. Once we land in a given part of speech, we emit a word, again probabilistically. So here's a cartoon example of that. So we start in a start state, and in our start state we have some probabilities of transitioning to other words. So we have a 0.5 probability of transitioning to determiner, a 0.4 probability of transitioning to a proper noun. Let's say that we do that. Once we're in the proper noun state, we have a 0.8 probability of transitioning to the verb state. If we land in the verb state, we have a 0.5 probability of transitioning to the stop state. If we are in the verb state, we also have a 0.25 probability of going back to the proper noun state. So this tells us what part of speech sequence generates our sentence. But what's more is that we also generate a sequence of words with every part of speech. So once we're in the proper noun state, we're likely to generate words like Tom, John, Mary, Alice, Jerry. If we're in the determiner state, we're likely to generate words like the, or that. Similarly, for the common nouns, we can generate words like cat, dog, bed, car, pen, apple. And so notice that there's no except state, unlike the finite states transducers that we were talking about before. We generate strings and we assume that any string that we can generate is part of our language, but some strings have higher probability than others. Okay, so that was sort of a cartoon picture of what hidden Markov models are. Let's go through this a little more formally. Okay, so assume that you have k parts of speech and a dictionary lexicon of size v, and you have some observations, x1 to xn, these are your words, and a series of unobserved states, z1 through zn. These are your parts of speech. We assume that we have a distribution over start states, and this is a vector of length k, that tells us what is the probability of having I as our first part of speech in a sentence. We also have a transition matrix that tells us what is the probability if you're in state I at time n-1 that you'll be in state j at time n. And we also have an emission matrix, beta, that tells you what is the probability of emitting a particular word w given that you're in state j. And so all of these things together define a joint probability over a sequence of part of speech tags z and observations x. And one of the exercises that we'll be doing in class is to compute the joint probability of a sequence given one hidden Markov model. What I want to talk about now, however, is two problems that are a little bit more realistic. So, given a bunch of data, how do you estimate a model? The other problem is, once you have a model, how do you then take unlabeled data and tag it with part-of-speech tags? So let's first talk about estimation. So remember, we talked about how you estimate a multinomial distribution using smoothing terms alpha or a pseudo count. And remember, when this is 1, we call this Laplace smoothing, and it corresponds to a uniform prior over all multinomial distributions. We'll use a smaller amount of smoothing for these examples. In this case, we'll use 0.1 as our smoothing. Okay, so we want to estimate some probability distributions. So here we have observations x. So these are the words that we observed. So here come old flat top is one sentence, one x that we observe. And we also observed some z's, the actual part of speech sequence associated with these sentences. And we have a total of 4 sentences in our corpus. So this is just a toy example. Obviously, if you're working on real data, you would have a much larger number of sentences. Let's say that we want to estimate the initial probability pi of starting in a particular part of speech. So we have 4 sentences. We have 4 parts of speech that we observe starting sentences. These are a modifier, a determiner, a conjunction, and a verb. So each of those have a count of 1, and when we add in the smoothing, those have a frequency of 1.1. Anything that we haven't observed gets a frequency of 0.1, because that's 0 plus 0.1. When we normalize that, we get the following probabilities. So this is our initial probability pi. So now what we want to do is we want to look at transition probabilities. So let's take a look at the transition probability for the verbs. So what we do is we look at all of the verbs, and then we look at all of the things that come after verbs. And we collect those counts. So we observe the following transitions. Verb goes to modifier, verb goes to conjunction, verb goes to verb, verb goes to pronoun, and verb goes to pronoun again. So we get some counts, we add in our smoothing, we normalize it, and we get the probability estimates that you see here. And we do the same thing for every part of speech, and this gives us a k by k matrix of conditional probabilities. What is the probability of going from one part of speech given that you were in another? So the last thing that we want to do is we want to estimate the emission probabilities. And again, let's focus on the verbs. And we'll take all of the words that we saw given that we were in a verb state. So if we do this, we do the same thing that we did before. We take in the counts, we add them up, we add in the smoothing, normalize it, and we get a probability estimate. So now we have a pi, a theta, and a beta. This is all that we need to define a hidden Markov model. And so the next problem, now that we've estimated our model, is how do you take a sequence of words, x1 to xl, and find out the sequence of part-of-speech tags, z1 to zl, that has the highest probability. And the process for figuring that out is called the Viterbi algorithm. And so it's impossible to compute all of the k to the l possible sequences. So what we're going to do instead is use dynamic programming to compute the best sequence for each subsequence going from 0 to time t that ends in a particular state k. And so if you haven't seen dynamic programming before, it's a very common tool that's used in computer science to sort of break down big problems into smaller problems and save some computation by reusing solutions. So typically what you do in a dynamic programming setup is that you have some base case. So you can find the solution very easily to small chunks of your problem. So in this case, what is the best probability that we can get given that we have a sequence that ends in part of speech K at time 1? So we've observed one word, the first word. What is the highest probability sequence of part of speech tags that gets us to that point? So that's simple. We don't have any choice in the matter. At time 1, we're in state K whether we like it or not. So we just compute the probability of being there. There's no choice. We compute the probability of being in state K at time 1, and that's simple. We just multiply our initial probability of that state by the probability of observing the first word in that state. So now once we have the base case, we can do recursion to find out all of the other states. So if we want to find out what is the best probability that we can get by some sequence of part of speech tags ending up in state K at time n, we look over all of the other part of speech tags, J, that could have gotten us there. And so we multiply the probability of the solution that we had at the previous time, n minus 1, times the transition probability of going from J to K, and then multiply that by the probability of observing the word that we saw at this position in, given that we're in state K. The complexity of this algorithm is k squared L. And it's k squared L because we have a table of size k times L. And in order to fill each of those cells, we need to look at the k previous states. And in class, we'll work through an example why you need all those k times L table cells using a phenomenon called garden pathing. But computing the maximum isn't enough. You also need to remember the best state that you came from. And so this is often referred to as breadcrumbs. So now let's look at an example of figuring out the optimal part of speech sequence for the sentence "come and get it," given the hidden Markov model that we estimated before. So let's start with the base case. So we want to figure out what is the best sequence that could get us to each of our part of speech tags at time 1. So again, this is easy. This is our base case. We multiply the initial probability, pi, times the emission probability for the word come for each of our part of speech tags. And so this gives us the probabilities that you see in the rightmost column here. But you've noticed that I've taken the log of this. So why did I take the log of the probabilities? So one, we're going to be comparing a lot of probabilities here. And it's easier to tell whether a number is larger or not when you've taken the log if it's a very small number, because otherwise you're just counting zeros. In terms of computer representation, it also makes it a little more convenient because underflow is less of an issue, and addition is cheaper than multiplication. And we can just add these logarithms instead of multiplying the probabilities because log of a times b is equal to the log of a plus the log of b. So we can add the logs of our probabilities rather than multiplying them. If you look at our base case, you see that the most likely part of speech tag for observing the sequence come is that come is a verb. And so you can see that the highest number in the rightmost column is negative 3.56. This is the highest probability sequence of part of speech tags that explain the observation come. Okay, let's extend our dynamic program one more step. So what we want to do is we want to figure out what is the highest probability part of speech sequence that can get us to time 2 And we'll need to do this for every part of speech, but first we'll do it for the part of speech conjunction. So first, we look at all of the places that we could have come from, all of the previous parts of speech. And then we multiply the score for the previous entry in the chart by the transition probability of going from that part of speech to conjunction. For example, if we started from verb and then we move to conjunction, we look up that probability in the transition table, we get some value, it's negative 1.65. We add those things together, and so once we've done that, we see that we don't need to bother with pronoun, preposition, or noun, because that's always going to give us a worse score than negative 5.21. And since we only care about the max, we can just ignore those. We do need to compute it for the other guys, but still, we don't get anything higher than negative 5.21. So the best way of getting to time 2 in the conjunction part of speech tag is coming from the verb. And so now we multiply the probability that we had there by the probability of observing the word and, given that we're in the conjunction state. And since we're working in log space, that's actually an addition. And that gives us negative 5.21 plus negative 0.81, which gives us a final score for the conjunction part of speech tag at time 2. And now we record the breadcrumb for that position, that when we're in the conjunction part of speech tag at time 2, our best previous state was the verb. And we continue to fill out the table. At the next time step, time equals 3, the best part of speech tag to explain this sequence is the verb, with the breadcrumb pointing back to the previous conjunction. And at the final time step, time equals 4, the best previous breadcrumb is the verb. And so when we want to figure out the best part of speech tag sequence for the entire sentence, we look at the very last time step, find the element in that column with the highest probability, and then follow the breadcrumbs back. In this case, the highest probability subsequence ends in a pronoun. And then we follow the breadcrumbs back in reverse order, which gives us verb, conjunction, verb. And then we put it all together and get that the best part of speech sequence for the sentence, come and get it, is verb, conjunction, verb, pronoun. The last thing that I want to talk about is using some simpler taggers in NLTK. So one of the first things that you can do is just write a rule-based tagger. And so you can write regular expressions, and if the regular expression matches a word, you can say which part of speech should be applied. And if you apply this to the Brown corpus and ask it to compute the accuracy, you don't do so well. You get 0.18 accuracy. But you can also train taggers from data. This computes the most likely part of speech tag for every unigram. Then, given an unknown sentence, it looks up what is the most likely part of speech tag for this word. And so this does fairly well. Depending on how much data you use, you can get somewhere between 73 and 76% accuracy. You can also do something more complicated. For example, you can use a bigram tagger, which uses pairs of words rather than single words. But remember from our language modeling lecture that there are lots and lots of possible bigrams, and you're not going to see many of them twice. So this has very sparse coverage. It only has 10% accuracy or so, but you can expect that these would probably be fairly accurate guesses. But you can combine these models together. So you can say, if we see something from the bigram model, great, we'll trust that, and then back off to the unigram model. This is similar to the back off concepts that we talked about for the language modeling lecture. And here you get a better accuracy, around 78%. This is the best we've seen so far, and you can create more complicated combinations of these taggers to get even better. So to wrap up, we talked about part of speech tagging, an important pre-processing step in natural language processing. We focused on the hidden Markov model, a statistical tool that's used for many different purposes, not just part of speech tagging. So I encourage you to read up on the other uses of hidden Markov models in the book, such as speech recognition, information extraction, and robotics. We also talked about simpler taggers in NLTK that, at least for English, get the job done. And in class, we'll work through some more examples on hidden Markov models and answer any questions you have about the homework.